Okay. So I'm very happy to welcome you to this week's Quantum Fluids and Isolation seminar. So this week we have Professor Aditi Mitra from NYU speaking. So Professor Mitra got her Bachelor of Science degree from Presidency Unit College in Calcutta, India in 1993. She got a master's degree at the Indian Institute of Technology in Kanpur, India in 1995. She got her PhD from Indiana University in Bloomington, Indiana in 2002. And at the postdocing at Columbia University and University of Toronto, she is now Professor of Physics at NYU starting in 2006 to present. She is a Fellow of APS in 2018, and she was a Simons Fellow in 2013. And today she'll be talking about the transport properties of a transient superconductor. So if you have any questions, please feel free to unmute yourself, and please feel free to unmute yourself or to clap in person or just clap virtually to welcome Professor Aditi Mitra.
Okay, well, thanks very much for this opportunity to give a talk. Again, I welcome questions during the talk, so I don't mind interrupting. Okay, so the title of my talk is Transport Properties of a Transient Superconductor. And this is work which was entirely done really by a brilliant postdoc who I was very lucky came to work with me, Yona Lemonic. My only regret is that he ended up working in Oracle. He's working in Oracle right now, but he was very productive, and everything I'll talk about already appear in these 5 publications. Okay, so as the title suggests, I'm interested in non-equilibrium phenomena in superconducting systems, and non-equilibrium superconductors, of course, is a very old topic, has a long history. There are even books called non-equilibrium superconductivity. But there are now new category of experiments that are being done, which are forcing us theorists to revisit the problem in a fresh way. And I will just outline one experiment that really motivated our work. And actually, the person who did this experiment is actually very close to where you folks are. He's Aditi Mitra, who's at Harvard now. So this experiment was done by Matteo when he was a postdoc with Andrea Cavalieri in Max Planck Institute in Hamburg. And the experiment is on this material known as K3C60. Now, K3C60 is a system that goes from normal to superconducting at a temperature of about 20 Kelvin. As such, there is nothing very exotic about the superconducting properties of the system. It is supposed to be a phonon-mediated superconductor and things like that. But what these people did is that they showed that by exciting some vibrational modes of the system optically, they can actually make this material behave like a superconductor at temperatures which are higher than the superconducting transition temperature. So that's why this experiment, when it was done, excited a lot of people because obviously if you can kind of raise the TC of a superconducting material, that's really fantastic. And what these people are proposing is a non-equilibrium way to raise the TC. So let me just walk you through what the experiment was about. So this is the crystal structure of K3C60. And these slides actually just show the equilibrium properties of K3C60. And in particular, it shows the reflectivity of K360, the optical part of the optical conductivity of K3C60 at 2 different temperatures. The red line is at a temperature greater than the critical temperature, so about 25 Kelvin, whereas the blue line is at a temperature less than the critical temperature at about 10 Kelvin. So this is a classic experiment which shows you how optically you can see a material go from normal to superconducting as you lower the temperature. So the red line is temperature greater than TC, as I mentioned, and the blue line is temperature less than TC. And so the signature of the system becoming superconducting is as follows, that the low frequency reflectivity of the system increases to unity. So the system becomes perfectly reflecting at low frequencies. then the real part of the optical conductivity drops down to 0 at a range of frequency, which is of the order of the superconducting gap. If you could have done a DC transport measurement, you would also see a Drude peak here, a delta function peak. But remember that this is an optical experiment, so you don't have access to very low frequencies, so you don't see the Drude peak here. But the signature of superconductivity, therefore, in these optical experiments is this suppression of the real part of conductivity at low frequencies, indicating the opening up of a superconducting gap. And then the second plot here is showing the imaginary part of the optical conductivity, and the signature of becoming superconducting is that the imaginary part of the optical conductivity shows a peak which goes as 1 over omega. And this 1 over omega peak can be understood very simply by just taking a Drude model for a metal. So Drude model of the metal would predict that the imaginary part of the Drude conductivity is sigma naught omega tau over 1 plus omega square tau square. Tau is some scattering rate. And you can loosely say that in a superconductor, the scattering time is becoming very, very long. And if tau is becoming very large, you can see that imaginary part of sigma goes as 1 over omega. So the appearance of a 1 over omega peak enhancement in the imaginary part of the optical conductivity is also a signature of the appearance of a dissipationless state, like a superconductor. So this is all equilibrium. And now these slides are showing how the reflectance of the sample, the real part of the optical conductivity, and the imaginary part of the optical conductivity are getting modified in the experiment that was done out of equilibrium. So in this experiment, what they do is that they initially take the system to be at a temperature above the critical temperature. So you can see that there are two different temperatures here, 25 Kelvin and 100 Kelvin. The red lines correspond to the optical properties at these temperatures. And the blue line is what they see after they excite the system with a strong pump. And they claim that the pump is exciting some vibrational degree of freedom of K3C60. And the surprising result is that after this excitation, instead of the system just heating, it actually begins to show a signal very similar to that of a superconductor. So notice how the real part of the reflectance is peaking to a value close to 1. Then the real part of the optical conductivity is getting suppressed at low frequencies, kind of indicating that there's some kind of a gap opening. And then the imaginary part of the optical conductivity is showing a 1 over omega type enhancement, which, as I explained in the previous slide, indicates that there is a state appearing here where the scattering rate is getting really suppressed. The scattering time is becoming very long. So the interpretation of this result was that somehow this shining, exciting these the underlying vibrational modes is enhancing the TC in the system. And even though the starting temperature was greater than the TC, in the absence of the pump, where once you shine the pump, somehow you are making the system become unstable to forming a superconductor. But of course, to really call the system a superconductor, you have to do many other experiments, right? You have to actually also do a DC transport measurement, which will unambiguously show the Drude peak at 0 frequency that I was mentioning. And of course, the smoking gun is that you should put the material in a magnetic field and see the magnetic field being repelled. But these experiments are difficult to do because one problem with the state that's created by shining the system with a strong pump is that the state only lives for about 2 to 10 picoseconds. So if you keep the pump on for a very long period of time, that's not good because then eventually the system will really heat, right? So you want to prevent heating, can't keep the pump on for too long. And then once the pump is switched off, then of course the lattice vibrations, if they're being excited as the experimentalists think, they will just relax back to thermal equilibrium within a few nanoseconds and the state is gone. And a few nanoseconds is too short a time to actually do all these other experiments. So you want so because this is a transient state, it's difficult to really tell, do the classic experiments related to superconductivity. Nevertheless, this experiment and several others from the same group and others have caused a lot of excitement among the theoretical community. And there are all these papers here. There are even more now. I'm sorry, the slide is not terribly up to date, which argue how by pumping the system, pumping the phonons, you can enhance DC. And the arguments are something along these lines. Some of these papers argue that when you excite a phonon mode of, say, K360 or some other material, it's like some kind of flow K excitation. For the electronic degrees of freedom, it looks like the underlying lattice is being periodically modulated. And then we know that that you have so-called flow K band engineering. It can have an effect of giving you a band structure which is relatively flat, and that can enhance the effective Hubbard U, right? Because the important quantity here is the ratio of Hubbard U versus the bandwidth. So that's one kind of way to argue how exciting an underlying phonon mode can enhance TC. Then there's another proposal, for example, by the Columbia group, which says that if you have phonon-mediated superconductivity, if you can somehow make the phonons that are mediating the superconductivity, if you can make them, if you put the phonons in a non-equilibrium state, like some kind of a squeeze state, then that can also effectively increase the strength of the electron-phonon coupling and can increase DC. So there are these kind of proposals, and there are, of course, other theoretical proposals here which claim that maybe these experiments are not seeing anything superconducting. And the argument is along the lines that you are applying a very strong pump to the system, and this can create a non-equilibrium instability. The instability that, for example, these papers have in mind is one where the resistivity of the system actually becomes negative. And if the resistivity of the system becomes negative, then you can imagine that you have a system where current carrying domains form, and in these domains, the currents increase in time. And if you have these kind of current carrying patterns, then when you do an optics measurement, it'll look very similar. It'll look like the system is becoming more reflecting and so on and so forth. So right now, it's difficult to really tell whether what is being observed is really a superconducting phase, or whether there is really some other explanation, like you are just creating a non-equilibrium instability, like these people are proposing. So with this background, the reason we set out to do what we did is we wanted to identify what are the signatures for the onset of superconductivity in a short-lived state. And secondly, we wanted to carry out a theoretical treatment which was simple as possible, in the sense that we don't want our answers to be too dependent on material parameters, because if it's too sensitive to that, then I just change a few couplings and I can get a wildly different result. So again, our goal is like, okay, let us just take the positive view on it and say that somehow the experimentalists can control the magnitude of the attractive Hubbard U. But the control parameter is such that you can only create a transient state that lives for a few picoseconds. So what would be the signature of the system being pushed into a superconducting phase in such a transient state? So that is our goal. And if we can say something specific, like, okay, in the current you will see these kind of signatures versus not that kind of signatures, then maybe it's helpful for the experimentalists going forward, because right now they don't really have a roadmap. They're just looking at the optical conductivity that they're getting out, and they're trying to make it look like a standard optical conductivity signal of a system in thermal equilibrium. But this is not a system in thermal equilibrium. It's a transient state. So can we say something about transport properties of such transient states? Okay, so with this background, the way we treat this problem is in a very classic way. We imagine we have an interacting electron system, and it's a closed system. We don't couple it to a reservoir or anything. And we imagine that the experiment can be thought of as some kind of a quantum quench. So in other words, we start with the initial state, which is that of electrons which are weakly interacting or non-interacting and in some non-zero temperature. So this initial state is a mixed state, and we time evolve the state with respect to a Hamiltonian which is interacting, and the parameters of the Hamiltonian are changing in time. So because in the experiment we think that maybe they have some control on the magnitude of the attractive Hubble-Dew, so we put all the time dependence on the magnitude of that attractive Hubble-Dew. And this HF, this Hamiltonian is such that it can, in principle, right, it can, in principle, support superconductivity in thermal equilibrium. But we want to just see what happens in the transient state. So just as a background, this kind of physics where you start with the initial state which has no order in it, like it's a normal state, and then you see whether how order develops if you are time evolving it with respect to a Hamiltonian which can support some kind of order, whether it be topological order or in our case superconducting order, or in other examples magnetic order, is very interesting to study. And you know, you can look at these review articles to see what kind of progress people have made in studying this problem. Anyway, so this is actually what this talk is going to be about. And let me just actually stop and see if there are any questions so far before I go into more details. Okay. Well, okay, if there aren't any questions, let me move forward. So now before I jump into again the details of what we do, let me talk about talk about a very classic problem that people kind of you can read about when you open like the textbook by Tinkham, and this is the problem of fluctuation conductivity. So it goes something like this. So let us say that my system is close to a superconducting instability. It has not become superconducting yet. Then we know that that in thermal equilibrium we can write the free energy of the system, right? So there is a part of the free energy which just represents normal electrons, and then there is a part which is the Ginsberg-Landau theory for the superconducting fluctuations. So this is a reasonable thing to write down if you are close to a superconducting instability, right? And so, in this situation, you can think that the conductivity of the system has actually two components. One is just the Drude conductivity for the normal electrons. And then there is another conductivity which is known as fluctuation conductivity. It is the conductivity which is arising from this part of the free energy, the Ginsberg-Landau part of this total free energy. And you can read about this fluctuation conductivity in various textbooks. I will give you a reference here. But let me walk you through how to determine this fluctuation conductivity, right? So, so what you do now is you add a little electric field to the system, right? Because you want to look at transport. But the moment you add a little electric field, you are driving the system out of equilibrium. So you need to now, so in other words, you applying an electric field, it will change the density of the superconducting fluctuations. And so you want to see how that density relaxes. So then to understand the relaxation of the superconducting fluctuations, you can kind of do it phenomenologically. There are microscopic ways also to argue it, but phenomenologically, you would probably open a review article like this one from the 70s by Halperin and Hornberg, who told you how do I model the relaxation of some order parameter. So let's assume that this order parameter is not conserved. Then you would look at this model A, which is, so if you open Halperin and Hornberg, there are a whole bunch of models, A, B, C, D, E, etc., depending upon what are the different conservation laws you want to keep track of. Let's say we take the simplest one where the superconducting fluctuations are not conserved. Then you will study its dynamics in the following way. So this is the electric field. This is just the non-conserved dynamics. And then there is a noise. And as long as you let me work with Ginsberg-Landau theory, where I'm keeping terms to quadratic order, I can solve the problem exactly. And I will arrive at how this density of superconducting fluctuations are evolving in time because of some electric field pulse. And indeed, from there, I can find out how the current is evolving in the following way, that the supercurrent is just simply 2 times the charge, because these are Cooper pair fluctuations, velocity of the Cooper pairs times the density of the Cooper pair fluctuations. And so when you do this little exercise, then you find that the fluctuation conductivity is this number here. And I've written this answer for D equal to 2. So this is a very classic result, but the main point for you to notice is that, first of all, it's a positive number. So what it's saying is that if I have the standard Drude conductivity, now if I put in the, take into account the fluctuations of the superconducting order parameter, then it gives an enhanced conductivity in the system. It's a positive conductivity. So what the fluctuations are doing is just providing a low resistance current carrying channel. And notice how this enhancement gets stronger and stronger as you approach TC. In fact, it's diverging exactly at T equal to TC. So our goal is kind of similar here. So in thermal equilibrium, we know, right, that from these very old results, that even though the system is not superconducting, as long as you're close to a superconducting instability, there are superconducting fluctuations around, and they enhance the conductivity. We want to explore what happens to this fluctuation conductivity in a non-equilibrium setup like that of a quantum quench. So that's really what I want to do here. Look at the quench version of this result. But I don't want to do something so simple as just making this A time dependent. You don't want to just, so somebody would ask, well, okay, I mean, this was a nice result. I think there are probably even experiments that have shown that you can see this prediction. Why not make A function of T and just, see what happens? Well, it's not a nice thing to do because, a transport is always a delicate problem. What we did, this calculation that I did just in one slide is actually not a conserving approximation. And I want to do a transport calculation which respects the conservation laws in the system, such as momentum, right? Because I want to, for example, apply it to a clean system. Also, it's very basic. Right now there's this simple linear time-dependent Ginsberg-Landau calculation doesn't really tell me how the electron density of states, or spectral properties of the electrons are likely to get modified, etc. So it was a nice textbook way to deal with the conductivity, but it's not really the correct way to go about doing things. So the roadmap for going forward is that I'll set up a study of transport, and if I have time, maybe tell you what the spectral properties look like for a clean interacting system, which is non-integrable, and I'll arrive at some kind of equation of motion for current. And I will make connections with Halper and Hohenberg models. So I don't want to say these models are ultimately still very useful, and I will make a connection to these models. Okay, and if I have time, I'll put in some disorder, but we'll see how this goes. Okay. So here is the specific thing that we do. Okay, so we have. I'm studying a quantum quench, so I have an initial Hamiltonian, which is just free electrons, where I occupy them according to a mixed state at a certain temperature. If I want to look at the conductivity, then it appears via a weak probe, A of T, entering in this kind of minimal coupling way. And the pump itself, which is supposed to be doing all the things that these experimentalists claim to be doing, which is modifying attractive Hubbard U, etc., is being modeled as this kind of quantum quench. So it's being modeled as a time-dependent attractive Hubbard U here. So there are two kinds of time dependencies here. A very strong one, which is the quantum quench that's happening. And then there is this weak one, which is just my linear response probe, which I'm going to use to determine what the optical conductivity in the system is. Okay, so delta, this is a classic four particle interaction written in a way where delta is just C up, C down. When its expectation value is 0, is non-zero, that means we're in a superconducting phase. But I'll always be in a situation where the average value of this quantity, the average value of the order parameter is 0. Rather, what will be important for us is a mod square of this quantity, which is basically the fluctuations of the superconducting order parameter. So our initial state is a normal state, and all throughout my theoretical treatment, I'll assume that the state stays in a normal state. So delta is always 0. The delta will be always 0, but the fluctuations will grow in time. And I'm interested in studying how they evolve. Now, of course, this problem is not exactly solvable, so we have to make some approximation somewhere. So what we do is we basically sum over all bubble diagrams. This is equivalent to doing RPA in the particle.
Can I ask a quick question?
Yes.
Is your assumption that the order parameter remains 0 consistent with the experiments that you started off describing?
That is an open question, right?
Okay, so are you going to try to argue that you can understand it just from fluctuations and you don't need a non-zero order parameter?
I'm going to argue that for the time period over which they're doing the experiments, it's too short to really claim that long-range order has developed.
Okay, thank you.
Yeah, so I'll show that in a few slides. There is actually this quantity known as critical slowing down. You're going from one phase to another. So it takes a long time for true long-range order to develop. And I'll try to give a time scale for that. And I'll argue that actually it's 2 picoseconds is too short a time.
Okay,
but
great.
I don't want to be gloomy about it. So what I'm claiming is that if maybe we should look at the fluctuation conductivity. That is the main thing. So I'm going to try and give you results for the fluctuation conductivity.
Okay, great, thanks.
Okay, so now at some point I have to make some approximations. So what we do is we do random phase approximation in the particle-particle channel. It's equivalent to just taking into account all loops like this. If I wanted to formally argue what I'm doing, what I can do is I can introduce an orbital degree of freedom in the electrons and make the orbital number of orbital quantum number be n, and then this is like an expansion in 1 over n. So this is not n going to infinity, but order 1 over n. Order 1 over n, you would require to keep all possible bubbles. If I try to put crosses here, there are like additional corrections. So that is the formal way to argue this. For people who who are really kind of comfortable with diagrams, there's also another name for these kind of this approximation is known as the GW approximation. And I want to be very clear that, I mean, as such, this GW approximation and RPA, these are things that people have tried to do and they've done it numerically and stuff, but we actually can make a lot of progress analytically because we want to be near the superconducting instability. So I'll tell you exactly how that allows us to utilize a separation of time scales and solve these problems, solve the dynamics analytically. So within this collection of loops, the self-energy is just this. It's a product of superconducting correlation D times an electron propagator G. And this D itself is U inverse minus pi. So basically this thing here is actually just a series of bubbles. So these are the diagrams we are keeping. The system is completely thermalizing, but we are interested in what's happening before the system thermalizes. So, again, even before you apply a weak probe, the system is out of equilibrium because we've done a quench, right? Our U is explicitly time dependent. So we have to solve this Schwinger-Keldysh equation. But now I want to mention that if I want to look at transport in this picture, then you have to make conserving approximation, which means that so we like to use this thing called the 2pi formalism, which is that the saddle point of this 2pi formalism is exactly this equation of motion. And then when you apply a little electric field, it shifts the saddle point. And so that's equivalent to, changing all the quantities here slightly to order the electric field. Anyway, so this is a technical problem, the technical point our papers discuss it, but I don't want to go into details here. But again, as I was warning you, this problem is a mess, but the reason why we make progress is because we identify the separation of energy scales here. Fermi energy is very large as compared to the temperature, which is itself very large as compared to this quantity R, which we call the detuning from the superconducting critical point. If you make this separation of energy scales, then you can argue that the electrons relax to thermal equilibrium very rapidly as compared to the superconducting fluctuations. In particular, the superconducting fluctuations, their equation of motion is given by some this particular equation. So without going into like technical details, you should think of F as just the density of superconducting fluctuations. And then what we find is that the density of superconducting fluctuations obeys this kind of an equation of motion. So this is like an overdamped dynamics del T. R is just the detuning from the critical point. Its explicit time dependence is because of the quench that we have done. And then Q is the wavelength of the superconducting fluctuation. T is the temperature, because I told you that we start with an electron gas at a non-zero temperature. And so you can see that at the end of the day, because of the separation of energy scales, this RPA is allowing us to write an equation of motion for the superconducting fluctuation that looks rather simple. It really looks like a time-dependent linearized Ginsberg-Landau theory. One thing you'll notice about this equation of motion is that there is no higher power in the superconducting fluctuations, and this is actually telling us that within that we are working in under the approximation that the superconducting fluctuations themselves are weakly interacting. So in some sense, this 1 over n expansion can be thought of as an expansion where you assume that the superconducting fluctuations are weakly interacting, and you can actually show when this weak interaction criterion breaks down. This is also known as the breakdown of the Ginsberg criterion. It breaks down when the density of superconducting fluctuations is it becomes of the order of this ratio, EF over T. So as long as the density of superconducting fluctuations is much smaller than this ratio, you are justified in assuming that the superconducting fluctuations are weakly interacting. And in the thermal equilibrium analog of this is just the Ginsberg criterion. Okay, now actually once you know this Ginsberg criterion, then like this person who just asked, what are we trying to say as far as the experiment is concerned? The first thing we can do is we can give a time scale for when the Ginsberg criterion is likely to get violated. So imagine you do a quench where you start in a normal phase, but the final Hamiltonian has a negative detuning. R is less than 0, which means that the superconducting order parameter fluctuations will keep growing exponentially in time, right? So then there will be a certain time where this superconducting fluctuation density becomes so large that the Ginsberg criterion is violated. So let's find what that time is. So F at T star is equal to EF over T. And then you can solve for T star and you'll get some result like this, 1 over RF, where RF is the final detuning, times log of EF over T. And then just plug in some numbers, right? So let's say the Tc minus T is say like 5 Kelvin, and EF over T is like 100 Kelvin. Then, sorry, EF over T is like 100. Then you'll get that this T star, which is the time at which the Ginsberg criterion is violated, is about a few picoseconds. So this simple exercise is enough to tell you that you cannot expect long-range order to develop in an experiment which is only long-lived for a few picoseconds, right? Because this time here, for long-range order to develop, the first thing is that the superconducting fluctuations have to grow so big that the Ginsberg criterion has to be violated. And then we do this simple back-of-the-envelope calculation, and you show that, and then you find that you're getting a number which is of the order of how long the experiment itself is living. So probably it's all right to assume that during the course of the experiment, long-range order doesn't develop. So then let me come to the part which says that—
one more question.
Yeah.
I mean, how critical is this point? So, you know, like a two-dimensional superconductor, you know, like lead in a very ultra-thin film, shows from the point of view of like STM, you know, a very clear BCS-like gap. even though there's no, long range order there.
Yeah.
But I mean, for the point of view of, transport or tunneling density of states or, any measurement that I'm aware of, it looks like a very robust superconductor without long range order. So, I mean, how important is this absence of long range order to it really behaving like a superconductor? I guess is my question.
Yeah, I mean, okay, I think, I mean, yeah, I understand what you're saying. Maybe, so the question you're asking, should I think of this as a 2D superconductor with no long range order? I think that this T star out here is, well, I mean, the point I'm trying to make here is that there is the phenomena of critical slowing down, which will prevent a true gap to open, right? So,
the clarification, 1 second.
yes.
You dealing with amplitude fluctuations, and a gentleman asked a question about a system dominated by phase fluctuations. And I think you have to rethink everything, for phase fluctuations.
Yeah, you're right. So right now I'm in a situation where it's really strongly amplitude fluctuations that are mattering here.
Okay, so in that sense, it's different.
Yes, in that sense, it's different. Yes.
Okay.
Yeah.
Okay, great. Thank you.
Yeah, you're welcome. Okay, so now let me come to the question of current. So then, as I was warning you all this time, transport is the delicate matter because, if I start with a system which is Galilean invariant, then, momentum is proportional to the velocity. And if I create a current carrying state by applying an electric field pulse initially, that current will never decay. So I'll always get infinite conductivity no matter what. So to do a reasonable computation for the current, I have to break Galilean invariance in some way. And the way we do it is that we impose an underlying lattice. We neglect umklapp processes, but it's just that the momentum and velocity are no longer proportional. So we have a current, which is, of course, still has a Drude peak when the part of the current which has overlap with the momentum. And then there's another which doesn't have overlap with the momentum and is decaying, and we look at the relaxation of that. So, so without going into details, essentially we break Galilean invariance via underlying lattice, and then taking the equations from this RPA within the particle-particle channel, we can massage the equations to make them look like this. So the J is the current, and delta J is, okay, so this is showing how the current is relaxing. E is the external electric field that has been applied in the system. And on the right-hand side, these are all telling you what is contributing to the decay of the current. So if I just look at the first term here, it has a very simple interpretation. This is just the Drude scattering rate. So if A was time independent and I didn't have all these terms, then just this term by itself would have said that the current decays exponentially with a relaxation rate of A over tau. And this time-dependent A of t is just saying that, okay, the way the relaxation is happening here is the electrons are scattering off of superconducting fluctuations, but the density of superconducting fluctuations are themselves evolving in time because I've done a quench. And so that's just giving me a time-dependent scattering rate. So that's what it means. So that's nothing special here. We could have just always argued the presence of that term, no problem. But what's special about the system are these memory terms. So the reason why these memory terms are arising is that when you apply, say, electric field pulse at a certain time t prime, it is changing, say, the density of superconducting fluctuations because these are charged. And secondly, these superconducting fluctuations, they relax very, very slowly, because I already argued to you that, okay, we are in a regime where the electrons relax really fast on a time scale of the temperature. And then these superconducting fluctuations, their time scale is determined by the detuning. And if that detuning is sufficiently small, then these superconducting fluctuations created at, say, some time t prime will influence the current at a time t much, much, much later. So that's why you end up getting these memory terms in this problem. It's entirely because of slowly relaxing superconducting fluctuations. So ultimately we get these equations and we can solve them. And I have to mention that you see these B, C's, they are not time translation invariant because they know about the quench. So I'm looking at linear response around out of equilibrium state. So that's why these kernels here are not time translation invariant. So we can just solve the problem, and solve at this level. We can solve this equation of motion, and I'm just showing you a plot, right, of how the what kind of result you'll get. So on the top here, this blue line is a quench trajectory. So R, which is the detuning, is being varied, changing in time in this particular way. So I'm starting with a positive R, and which means that I'm in the normal state. And then I change R, I make it negative for a certain period of time. So I go into the superconducting phase, and then I make it positive again. So for a transient period like that of the experiment, I am in this superconducting phase. And these other plots here are just showing how the superconducting fluctuations are evolving in time. These three different lines correspond to superconducting fluctuations at three different momenta. So Q equal to 0, superconducting fluctuation is of course the most important, and that corresponds to this orange line. And you can see that the superconducting fluctuations are growing, and they're strongly enhanced when this detuning is momentarily negative. And then when the detuning becomes positive, the superconducting fluctuation relaxes back and eventually goes to 0, because out here you are back again in the normal phase and you don't expect any superconducting fluctuations. So this is the meaning of the stop plot. What's plotted below is the solution of the kinetic equation for the current. And here I'm just plotting all the information in terms of a Drude scattering rate. The Drude scattering rate I'm defining as the ratio of imaginary part of sigma over omega times real part of sigma. So it's a frequency dependent quantity, and I'm plotting this Drude scattering rate for several different frequencies and as a function of time. So this time axis here it's roughly the same as this time axis. So what you see here is the following, that so let's focus on, say, this 0 frequency Drude scattering rate, right? So what you're seeing here, or maybe not 0 exactly, let's look at omega equal to 0.13 t, so like this orange line. So if there was, so what you find is the scattering rate is going up, superconducting fluctuation density is going up, scattering rate is also going up. Okay, nothing fantastic. That's not surprising. You're just creating more number of scatterers, and the system is scattering more efficiently, scattering rate is going up. But then you find that after a certain time, when the superconducting fluctuations have peaked, the scattering rate actually does go down. So it initially does increase and this goes down. After some time it goes down. And this suppression is really the signature of the superconducting fluctuations, because these superconducting fluctuations are themselves an efficient current carrying channel, and as a result, their presence actually increases the conductivity or reduces the scattering rate. And that's what you're seeing here. So, so that's one signature, that you have created superconducting fluctuations, that you will see the suppression of the Drude scattering rate in this transient way. And the other signature here is that look at the way the current actually relaxes back to thermal equilibrium. This relaxation is very slow. It goes as a power law. What power law you get depends on what dimension you are in, and in spatial dimension d equal to 2, this decay goes as 1 over t. It is weaker in higher dimension. So, so this would be like two signatures that you could look for, even though the system has not developed long range order. A suppressed Drude scattering rate and a very slow decay of the current would be signatures of approaching the superconducting transition. And you can also show various scaling collapse, and by looking at how the conductivity changes as a function of detuning and things like that. So let me not go into details like that. Let me actually talk about Halper and Hohenberg. So I showed you this equation of motion for the current, and a rather simple interpretation of the various time-dependent scattering rates. And the question again is whether the masters who wrote this very famous review article in the 1970s, whether we can still bring that to good use. And it turns out that yes, we can. So we can actually argue this equation of motion for the relaxation of the current by not working with Halpern-Hornberg model A, but using model F. So in model F, what you do is you take a order parameter, which is not conserved, but it is coupled to a conserved density. So the free energy you're working with is a little bit more complicated. It is the superconducting order parameter, and now you should couple the superconducting order parameter to some charge density. So this is the form of the coupling we've written here, delta square, which is superconducting fluctuation, and delta rho, which is say the electron density. So that's the free energy. And then when you want to look at the relaxation of various quantities, then model F says, okay, delta relaxes as though it's not conserved. So this would be the equation of motion. But the charge density itself should relax in a way which is conserving. So the equation of motion for delta rho should should obey the continuity equation. And so if I write down this kind of coupled equations, then I can actually get back the equation of motion for the current dynamics that I wrote down here. But it's just that our microscopic treatment allows us to determine what all those parameters are in the Ginsberg-Landau theory. So, sorry, in the Halpern-Hornberg model F dynamics. Okay, so that is as far as current in the clean system is concerned. Let me stop and see if I've asked any questions, because then I can just tell you the story with the imaginary part of the spectral density, what's happening there. But are there any questions so far about the current?
Maybe one more quick one.
Yeah, sure.
Are you going to tell us what you think are the definitive experiments to identify whether this scenario is applicable?
Well, so the definitive experiment would be to look at how your really do a time-dependent experiment, right? So right now there is no time dependence in their sigma of omega t.
Mm-hmm.
So you want to do sigma of omega t, and then you have to look for characteristic power law decays in sigma of omega t and transient suppression, enhancement and suppression of tau omega t as defined by this ratio. So you absolutely have to do a time-resolved experiment for the current. Right now, they don't have that.
Mm-hmm. They don't have that capability?
I suppose, I guess I don't want to put words in their mouth. I don't know what the situation there is.
Uh-huh. Okay, I mean, there's time-resolved photoemission. Is that easier than?
Oh, no, I don't think well, okay, time-resolved photoemission, is that easier? I don't know, I should probably ask, you should probably ask.
Okay, yeah, I know you're.
But, I mean, as a theorist, this is just a standard quantity to look at, right? You wouldn't just look at the current, you also want to look at what happens to the spectral density, right?
Mm-hmm.
Whether you can actually, whether this is an easier experiment than looking at sigma as a function of omega t, I don't know.
Right. No, I'm just trying to parse all the different pieces that are kind of out there in the community and how to kind of settle the scenario of what's really going on in these like pumped superconductors. So it sounds like your conclusion is that there are some new experiments, time-resolved optical conductivity that could be done that would give you information about whether your fluctuation scenario is likely what's happening.
Yeah. Mm-hmm. Yes.
Okay, great, thank you.
Yeah. Okay, so now let me look at let's talk about what happens to the electron, the imaginary part of the electron self-energy, right? So it's just telling you the scattering time. Here, the way the electrons are acquiring a lifetime is because of scattering off of Cooper pair fluctuations. And then you have a cartoon like this. So electron comes, it's and rear reflects into a hole, and a Cooper pair forms as a result of the scattering. And if the incoming electron has an energy which is very far from the Fermi energy, then this is a highly off-resonant process. And so any corrections to the electron lifetime will be small. But as the electron energy begins to approach the Fermi energy, then the scattering process becomes on shell and more important. So actually the lifetime, the way it behaves, the imaginary part of the electron electron self-energy, the way it behaves is opposite that of a Fermi liquid. So in a Fermi liquid, you expect that electrons that have an energy far from the Fermi energy scatter very rapidly, and electrons at the Fermi energy scatter hardly at all. But in this scenario, it's just the opposite. The electrons which are at the Fermi energy scatter very rapidly because the scattering is due to scattering off of superconducting fluctuations, and this process is resonant. So what Yona did is a calculation as to how the imaginary part of the electron self-energy at the Fermi energy grows as a function of time, and then for a quench, which is right to the critical point, you can show that this has some kind of a universal form, which is given in our paper. But the main story here is that that you expect the electron lifetime to be very non-Fermi liquid life because of the scattering of Cooper pair fluctuations. Okay, so I can in a few minutes I can also tell you what happens when you look at a system with disorder. So I looked at the clean system, but we can also look at a case where there is disorder. Then the calculations are a little less delicate because you can just do a Kubo formula computation for the optical conductivity using these very standard diagrams that were written down by Azlamazov-Larkin and Maki-Thompson a long time ago. So again, for aficionados, you may have encountered these standard diagrams for calculating the fluctuation conductivity, but this was again done for electrons in a disordered conductor. And what we set out to do is look at what happens to these Azlamazov-Larkin and Maki-Thompson corrections to the fluctuation conductivity when you've done a quench. And again, the reason why we could make progress was because we took into account that there may be a separation of energy scales in the problem where the electrons are relaxing on a time scale which is short, set by the temperature, whereas the superconducting fluctuations themselves are relaxing very slowly. And this allows us to compute some of these diagrams. And you can even get analytic expressions for the conductivity. So this is an expression for the conductivity for the case where we start from the normal phase and then you do a quench to the superconducting critical point. So this is a classical critical point. And as one expects for a critical point, all the results are universal and only depends on these two times, T1 and T2. So, so it's a very clean result. And of course, it would be great if you can actually do it you could see it in an experiment. And what's also kind of interesting is that maybe this is a point for experts. This first term here that I've written is what is known as the standard Azlamazov-Larkin. It is the quench version of the Azlamazov-Larkin fluctuation correction to the conductivity, while the second version is the quench version of the Maki-Thompson correction of the correction to the fluctuation conductivity. In equilibrium, these two corrections look very similar. Okay, the way they depend on T minus Tc is very similar. But in a quench, they are not so similar. And maybe this is one way, if you know what the scattering time in your experiment is, this would be one way to detect whether what you're seeing in your transient conductivity has any origin due to superconducting fluctuations or whether there's some other phenomena that is appearing there. So this is just what I think this is a good time to conclude. So what we've shown is that presented results for in interacting electron gas that traverses close to a superconducting critical point. Again, I should mention that we did all this near a classical critical point. And basically, we gave results for fluctuation conductivity and also time resolved RPIS. And what are some of the future directions? Well, I mean, of course, it's interesting to look at the coarsening regime when, you know, you have more number, when you have more number of slow modes. In our case, we had just one slow mode, but when you go into the, when you've stayed in the superconducting phase long enough, then, you know, you have domains perhaps and how they grow. This is an interesting problem. A very classic problem is worth pursuing. But actually right now I'm more interested in looking at revisiting transport in 1D non-integrable systems, because here it seems like even in the 1D case, there are a lot of open questions about what the conductivity looks like and things like that. Okay.
Okay, so we have time for maybe one quick question. Maybe one or two quick questions. So please either raise your hand or you can unmute yourself. So maybe I'll wait for 5 more seconds. I think a lot of the questions were asked during the talk.
Let me ask one more if no one's going to ask.
Sure.
I guess how much of this would carry over to a system where you're quenching into a different state, like a magnetic state, from like a non-magnetic state into a magnetic state? I mean, is there any kind of analog to the phenomenology?
Well, I mean, I think that the signature on charge transport will not be quite as spectacular, because we know that superconducting fluctuations are very special in that way, right? They're charged and they carry current.
Right.
But I mean, you can look at the analog on spin current, for example, if there was a way to measure spin current.
Yeah, I mean, I guess what about, like, you know, the structure factor? I don't know, is that?
Oh yeah, the structure factor, right. You mean, you mean the
S of k and omega. Like, suppose you had time resolved, neutron scattering or something like this. Yeah, no, I mean, those are interesting questions to look at. I think the formalism can certainly be used in that context, that I do not doubt at all. But I cannot tell off the top of my head what the functional forms of those quantities would be, right? But in some sense, this is touching upon this 1D problem I've been mentioning, because in 1D, you know, all charge and spin and everything are kind of coupled to each other. So in fact, we are currently now looking at how the structure factor, which is just what you asked, spin correlation function, would behave in exactly this kind of situation. I was a little worried to touch this problem, but apparently there are all these high temperature, you know, because this is a high temperature result. What we've done here, it's near the classical critical point, but now they're saying all these exotic predictions for transport at high temperatures in 1D systems. So I'm very interested in pursuing that line of study. So the structure factor you mentioned would have something interesting going with it, but I cannot tell off the top of my head right now. Okay, great. Well, yeah, thanks for a very interesting talk.
Oh, thanks, Greg.
Okay, so maybe if there are no further questions, let's thank Professor Mitra again.
Okay, well, thanks for listening.